Great start. Good. So what are engineered quantum systems? So engineered quantum systems are rather macroscopic systems. So they're made of a lot of atoms, but they still behave quantum mechanically. And the idea is that we want to use this quantumness for applications like quantum computation, sensing, and communication. And here we see some examples of devices. It's a bit biased, but these are devices my group is most familiar with. So we have something which is here is a superconducting qubit from Johann Pop's group at KIT. And on the right, we see also a qubit of 4 qubits on a chip from IBM. It's a bit older. Now they have like much bigger chips. And clearly what people want to do with these devices is quantum computation. But there's another form or platform, which perhaps some of you are not so familiar with, and we call optomechanical systems, and some 2 engineered systems below here, and they can live in the microwave world. So we have here a microwave circuit. This is a so-called drumhead resonator. So it's a capacitor with 1 moving plate, and this is a mechanical mode, which is coupled to the microwave field via radiation pressure like force. And the same kind of interaction is also found in this photonic crystal, different frequency regime, where we have here a beam, and the beam has holes punched into it, and the size of these holes varies, and then forms a cavity for mechanical excitation and as well as a photonic excitation. And these are just some examples. There are a lot of others, but just to give you my theory view of it, what we have with these systems is actually a box of quantum toys, which we can then use clearly for all these applications we want to do, but also to explore the fundamental aspect of quantum mechanics. We have a high control over these systems. And the way I see it, and this will hopefully help you for my talk, I think of them as blobs, okay? So if I use gray blobs through my talk, this is a general quantum system. This can be then an oscillator, this can be a qubit. And if I use a specific system, I will use this green-blue shading, and this can then, and then as an operator, and it can be an harmonic oscillator, or here, for example, a 2-level system, a qubit. Yeah, and to see if we all understood this, we can come back to the pictures we had. So this quantum system is, for example, if we have 1 qubit, this is just this 1 blob for me. And if we have the 4-qubit circuit, we have 4 qubits. And the nice thing about thinking in these blobs is actually that if we now take these optomechanical examples, they are in the end just 2 coupled harmonic oscillators, one mechanical one and one optical one. And although these 2 devices live in completely different frequency regimes, in the form of blobs, they are really just 2 coupled oscillators. And so if we start doing theory for these systems, we can start thinking about just these blobs or these harmonic oscillators, and then we can later on talk to experimentalists and think about the real world if you can implement protocols and applications in either platform or in both. So important is, so we have to clearly, or the experimentalists have to design these platforms in the lab. But what we also need to do, we need to be able to manipulate these systems, to control them, read them out. And this all has to happen at the quantum level. There's specific requirements. And so what is, for example, important if we think about a readout is that we have devices which can operate quantum limited. So here, for example, if we have a qubit, there's a chain here of different elements. Just to give you a hint, this is a circulator, which is a device which is non-reciprocal. We will come back to that later on, which routes signals just in one direction. And this should help to protect the qubit from everything from the outside, right? And then you see this next thing, something I normally talk a lot about. Today, I will not talk so much about it. And this is an amplifier, because if we have a quantum system and we extract information out of it, right? This information is often contained as a really, really weak microwave signal. So to get our big classy hands on it, we need to amplify the signal before we can actually go anywhere or do something. And these devices are in the best case quantum limited. Another important thing besides readout is also that we can couple these systems, right? So we need to get them into communication with each other. And this is one thing which we will talk about in a second a little bit. How can we actually couple these systems in a highly controlled manner? And as an important thing, the challenges of doing all these things is whatever you want to do, readout or coupling, is actually that you have to fight with dissipation, and you also have nonlinearity, which you do not want. And this is two ingredients which are bad, but I want to convince you today that actually both of these ingredients can also be like help you and can be used for good and can be a resource actually. But we will come back to that later on. Okay, so first of all, I want to say a couple of things about how can we couple these systems. So again, I'm starting now with two gray blobs, these general quantum systems. And I speak of a resonant coherent interaction if these two systems live somewhat on the same time scale, or have the same frequency, for example, same energy scale. And then we have perhaps an Hamiltonian, which describes the coupling between them, and this is resonant. However, we are often faced, or perhaps also wanted, the situation that our systems are not coupled in this way. So we are off resonant, so that they live on three different time scale or energy scale. For example, taking the optomechanical systems, there we have a mechanical mode, which is perhaps kilohertz or megahertz, while we have an optical mode, high terahertz, or microwave mode, gigahertz. So we have two systems which in principle don't talk to each other. But we want them to talk. So what we can do here is actually use something which is called parametric modulation, where we engineer resonant interactions. And to start off to how we can do this, we can use a really simple example. Now we go to these kinds of blobs. So we have now two oscillators and the first Hamiltonian. And we have here the first part just describing the energy, the free energy of these two oscillators. They are different in frequency, so they are non-degenerate. And we have them coupled in the simplest way we can couple them in a quadratic manner. And important is we have here a parametric modulation, like a time-dependent coupling. Okay, so first of all, what we do, we change our point of view. We go into an interaction frame with respect to the free Hamiltonian. So we remove the oscillation, and we have then just this Hamiltonian. So here's the recipe how to get there. So it's a unitary transformation. It's not so important, but important is that we now have here no longer this free Hamiltonian, but we have just these time-dependent oscillations here. And this is good because we can see that this first process here oscillates with the difference of the frequency of these two oscillators, while the second process actually with the sum. And this tells us already what kind of energy or modulation we have to put in to make one of these processes resonant. So if we have a periodic modulation, which is just one external perhaps microwave drive or a light field, where we have like a cosine, which has a certain amplitude, and we have here a frequency and perhaps a phase. And if we now choose this frequency exactly at this difference of these two oscillators, what we do if we just plug this in and then we just keep the terms which are slow, we can get here the frequency conversion process resonant, where you see now that this first process here, which is just a swapping of excitations, right? So you create an excitation in B while destroying an excitation in A. And this is resonant. And the nice thing about this periodic modulation is that the amplitude in front of this is actually controlling how strong we can do this process, right? So we have a control knob, that's what we want. And you also see that this phase here is showing up in the Hamiltonian. So we can also imprint a phase on this process, which is going to be important later on. And all the other terms you will get, which can be considered counter-rotating if you play your game right. Okay, this is the first process, but we had a second one, and this is if we modulate now at the sum of the two frequencies. So we can again get a process which we call parametric amplification, where you see here that we create two excitations. Again, we can control the strength of this process, and we can have a phase associated with it. And this gives us also an amplifier or two-mode squeezing for the experts. Okay, so this is still pretty abstract, right? So how can we actually get these interactions? And there are different examples, and the first one I would like to give you is how we can do this in superconducting circuits. And I still give you a theorist view, right? So don't ask me about the details. For me, this is all similar, like kind of game. So you have circuit loops made of superconducting material, which are intersected with Josephson junctions. Just see here. And these loops provide nonlinearity and provide us with the possibility to, if we couple oscillators or qubit to it, to have a parametric modulated coupling, which we can control. So we drive, these are all different design choices. We drive either with, I don't know, through flux through the loop, or we drive it from the outside. And then we can use them as mixing elements and allow for controlled coupling between linear and nonlinear oscillators. And this is pretty neat because we can, with that, engineer these resonant processes. And you can, these are just some examples of what things you could do with this. So clearly the first thing you can think of is just engineering a coherent process, you know, just going back to the example of the two oscillators, right? You can get such a coupling. You can also think of becoming more crazy and couple more things to the same modulator and get higher order processes. It's more challenging. Or you can also think about doing this on or like on a lattice, right? Where you have now actually a network of, for example, qubits, right? This is in the end, like this would be great if we could have this as a, you know, as a chip for doing quantum computation, because here we have a good control about the coupling between different nodes. And this is the next thing is a dissipative process, and we will come back to that in a second. But first of all, I want to make the point that these engineered resonant interaction via parametric modulation are a really powerful tool. And because we can turn on and off interactions between two systems via high dynamic range, is great. We can also create particle non-conserving interaction because we provide energy from the outside, and we can get these higher order interaction. Okay, so, but on the slide before, I talked about dissipative process. And I also promised to tell you something about how we can use dissipation for something good. Which is counterintuitive. Normally, we just want to avoid dissipation. And this is, normally we have the situation, right? We have our like general system, quantum system, and it's coupled to the environment above. And what happens is that we lose information into the above, and we decohere, and it's really bad if we want to do any kind of quantum application. The normal way, or one way of modeling such a system is something which we do within open quantum systems theory by using a so-called master equation. Nothing too fancy. If this is new, just ignore it. It's just a way to, we will see a couple of them, but in the end, this is just the evolution of your state, of your density matrix under the influence of an environment. And so besides having your normal Hamiltonian part, you will get something which we call a dissipator, a Lindblad operator, where you see the form here is given as that. This is, you make a couple of approximation, right, to arrive here, and not every bath is actually fall into, or we can model not every bath within this framework, but for a lot of systems and baths, it works out. And if you look at this kind of super operator, it's different than normal, because you have here a term which we call a jump operator, where we have the operator acting from left and right onto our density matrix, and we have something which we call continuous evolution, which is just there to preserve our probability. But this is just the standard way how we could model a dissipative path. And then here the set is here this jump operator, where we actually have here, I indicate this as such that in this kind of way we have this jump operator would be a system A operator. And this would be a situation where, you know, you don't have any advantage of the dissipation. But that's not what I want, right? So what I want is a different situation. And I want to have engineered dissipation where I have a certain control. So I'm extending my system. Right? This is one way of doing it. My main system is still A, but I couple it control to my system B. Yeah, so this is an indicating that I have here a certain control. But the system B is coupled to the environment. Yeah, so the Lindblad term here would now involve a system B operator. And now you can think of it as, if I'm in the perspective of system A, like a door, right? I can control this coupling. So now I can open and close this coupling and see how much dissipation I get. And then I can do nice things, like, for example, get my system into a target state, which is not trivial or something like that. Okay, so this is just a basic concept of how one can think of engineered dissipation. But what is also interesting is to think about the dissipative processes. Yeah, that's how we phrase this. So now the situation is slightly changed. We have now system A and system B, and these are our main systems, but we couple them in a controlled manner to our system C, which is coupled to dissipation, to an environment, to the bath. And if this is really like strongly damped system, what we can do, we can actually eliminate it and obtain this dissipative coupling, where now we have a special form of our jump operator, which is now a system A and system B operator. And this kind of dissipator here with this such a jump operator couples system A and system B. Okay. So this is what we call engineering a dissipative process. And I want to keep it basic. So I want to show you, yeah, there's also a coherent coupling, actually discuss an example. And going back to exactly the example we had before, we have two oscillators, A and B. They are coupled via this auxiliary oscillator. Yeah, and here this is the Hamiltonian describing this. I take the simplest form, so we assume that this coupling here is modulated at a frequency difference. So we have frequency conversion or hopping between oscillator A and C and B, which is just given here. And then we assume that we will have some dissipation on our mode C. And I account for some detuning to make the story complete for the mode C. Okay, so if we now go and assume that the damping is really strong, we can eliminate mode C adiabatically and arrive at a master equation, which this row is just describing system A and system B, the state of system A and B. And then you get what I said, you get a kind of dissipative coupling where you have now a dissipator which involves system A and system B. And this kind of dissipator does not only lead to like the dissipation of the individual local dissipation in the individual system, but it also couples system A and system B. Similarly, that's why I also kept this detunings apart, which is sometimes forgotten. If you couple via an auxiliary system, you can also get the coherent coupling. And this is then here a coupling which you see scales with this delta, which also provides us with a small, like a local effect, which is a frequency shift, and some hopping between mode A and mode B. Okay, so this is how we can engineer indirect processes. And now the question I want to answer in the next 5 minutes is what happens if we actually combine a coherent and dissipative process, and can we then have an advantage due to the dissipative process? And this is something which is, again, a picture, right? We have two system A and system B. We couple it via coherent interaction and via a dissipative process, yeah, which is here illustrated as an engineered reservoir. People also use the different words for terminology like engineered dissipation, engineered reservoir for these kind of things. And I want to show you in the next minute that if I do my job right, so I balance my coherent interaction and the corresponding dissipative interaction, that we can achieve non-reciprocity. And so I break the symmetry of reciprocity. And if you want to know more, this PRX it's a bit older, but introduces this method. But first of all, what do I mean when I speak about, or when I think about like breaking the symmetry of reciprocity? So again, general simple system, but we have now a really specific situation and a non-reciprocal coupling between system A and system B. For example, in that way that system A talks to system B, but not the other way around. It's a non-reciprocal situation. And this is the situation we want to engineer. And why should you care about non-reciprocity? So if we take another example from actual experiments, so here you see an older picture from 2018, again, IBM, where it's from the press release, where they have inside of this magnetic chamber is supposed to be the chip with the qubits, right? But the important thing for us now is just to look at the outside. So here you see all these boxes right? And these are circulators and isolators, non-reciprocal devices which route the signals to the chip and away from the chip. And what you can see that you need a lot of them. And this is actually challenging because you run out of space. And they are also not the greatest devices because they are lossy. They are based on a magneto-optical effect, so they need magnetic fields. You don't want to have that close to your qubit. And plus bulky. So people have started to think about how can we actually get different kind of devices, or how can we engineer non-reciprocity without using magnetic fields, and in such a way that we can implement them on chip. And there has been a lot of activities, and I know that this is not a complete list anymore. So if somebody knows all the complete list, I apologize. But this is just to give you an idea about the experiments which have been done in the last 5 years, or 7 years, actually. So, and there was some realization coming from the superconducting circuit implementation, where we have, again, our magical ring, like here, for example, a Josephson parametric converter, which mixes 3 modes. You drive the system in the right manner, then you obtain non-reciprocal transmission with and without gain. As I said, as a theorist, these magical loops are all a little bit the same. So here's a GPC, it's a loop with 4 junctions. You can do the same game with just 2 junctions and use a squid. And this was from the NIST group in Boulder a couple of years later. And also the optomechanics community was really active in the last years. Here there's a little bit of a different kind of architecture, but in the end you use now like 4 mode systems with 2 mechanical modes and two cavity modes to realize non-reciprocity. And what it boils down to in all these examples is that what you use is actually parametric modulation to control the coupling between the modes, and you engineer a synthetic magnetic field by controlling the phases of your drives you apply. Okay, so this has been really active, and what I want to show you now that we have found like this really general recipe how we can think of these implementations and how we can engineer non-reciprocity. And again, we have a master equation. Again, we have general systems, gray blobs, right? A and B. And what we do, we combine a coherent coupling of this form. So A and B are really general system operators. I haven't specified this further. And we combine this with this dissipative coupling. And they have a different strength. We have a gamma here for our dissipative process and the lambda here for our coherent coupling. And I have a phase here. The phase is important. This is our synthetic magnetic field. It doesn't have to be in the dissipator. It could also be here, right? Important is just that we have a physical phase in the end. So, and I will tell you right away how to do now. How can we render the system non-reciprocal? We just have to balance our strength of our processes, and we have to set the phase to the right value. So, and the sign here, plus or minus, will determine the direction in which we go. And to see that this actually works, we can just take a look at the dynamics of expectation values for arbitrary system operators, right? So system operator A and B. And I already applied the directionality conditions in such a way that we have a non-reciprocal interaction, that system B is driven by system A, but not the other way around. And you can see that if I look at the dynamics of A, I really just have some local effects here, while system B has local effects, plus it gets the information of system A. So, and if you would have changed the phase here, you would have the reverse situation. And this is a really powerful recipe which we can apply. It's really general to realize directional interactions between 2 systems. And we have done like a lot of work in this direction. First of all, thinking a lot about, how can we design non-reciprocal devices? And this is perhaps like the first 3 references here where we think about how we can design directional amplifiers. How can we understand this recipe of non-reciprocity? And how can we be more efficient if we think about like resource efficiency using less pumps to realize our systems? In the recent years with my group in Berlin, when I was still in Berlin, we started to think about also using now non-reciprocity beyond signal processing, right? Not only non-reciprocal devices, but can it be a resource for other things? And We have just two recent preprints which show that non-reciprocity is actually really interesting if you think about entanglement generation or also about time-delayed quantum feedback. And if you're interested, I can see it. Okay, so, but this is also not limited to like few mode systems. We can also think about lattices, and this was some work I did when I was in Princeton with Hakan Terecci. And here we see that we can also use this recipe to route signals in a network of oscillators, and you have like full control about how and where you go in your lattice, as you can see, right? You have a two-port device. You can go along one edge, two edges, or in a weird manner. And the thing is that this is not something like an edge state, which people have perhaps seen. It's really a locally controlled path you can design. And so if you then think about coupling multiple elements, you can really use this as a router or a switch in the lab. And this is not only theory. We had a couple of variations, for example, in this group about a non-reciprocal amplifier, where we can apply this recipe. And the nice thing is, when I gave you the recipe, I told you that we have this kind of, I said I didn't say Markovian limit, but there was a Markovian limit where we actually think only in this master equation level of this dissipator. But this is actually not only necessary, as we showed here in collaboration with Oscar Painter's group at Caltech, where we have an optomechanical implementation, where we showed that actually this recipe still works if we do not go to this Markovian limit. Okay, so this is an example of an optomechanical system. And this is something, or we will focus in the next minutes only on optomechanics. And I will change gears. And also, if you have fallen asleep till at the moment, it's a chance now, I will be some basics now to wake up again and then fall asleep again. Okay. Optomechanics, coupling of a cavity of a photonic field trapped between two mirrors, for example, to a mechanical mode. This is a field which is really rich. It has a lot of different platforms. Not like in my head, they're just two blobs, but in the real world, there are huge differences between systems, right? So in terms of length scale, they can be really small. We have seen the microwave device, but also we can have different designs where we have a mechanical element in the middle of a cavity, or also like if perhaps you know this, that LIGO, the gravitational wave detection, the readout of the signal is also based on an optomechanical effect. And this is like a huge variety. It's just a couple of examples of how where we can find optomechanical interaction. Okay, and what can we do with them? A lot of things. Mechanics are such great systems because they talk to so many things. Right? They can talk to high terahertz frequency photons. They can also talk to microwave modes, and are really then good candidate for transducers, which are really important if you think about quantum communication networks. They are also really sensitive, right? So we want to use them for sensing of small forces and precision measurement. And there's a lot of different kind of things people want to do in terms of application, but also in terms of studying, like for example, the quantum to classical transition, or also nonlinear dynamics. So there's a lot of examples, and it's a great field. But back to the Hamiltonians. So this is the general form of an optomechanical interaction, right? The simplest example is really like a Fabry-Perot cavity, and one of the mirrors can move. And first of all, what we have is again a free energy of a cavity mode, and mechanics. They're most likely, or in most cases, really different in frequency, and they are coupled via this optomechanical or radiation pressure-like coupling. You see here that in the end, what this is you have a photon which imprints a force on your mechanics and displaces it, and in the same form, a displacement of your mechanics will change your frequency of a cavity. And so this is then also how this G comes about. This is in the end an optical shift per displacement. And this is what you find in all these systems. And these systems are, again, also, we can't look at them without thinking also about dissipation. And so we have dissipation in our mechanics, as well as, for example, could have intracavity losses, but we also have losses because we need to couple this cavity to the outside world. So we drive it, meaning we have a kappa external. So And the drive is important because we want to control the, like it's again a parametric control, the mechanical coupling between the mechanics and the cavity. And this is just how we would normally model a drive. And then we have a time-dependent Hamiltonian. A way to get rid of this really fast is simply rotating again. And then we will have this delta here as a detuning between our drive and our cavity frequency. Okay, so this is the general form of optomechanical interaction. This G here is in principle for most setups really small, yeah, which is good and bad. Yeah. But for most applications for the moment, what people will do is actually a linearization. So you linearize your cavity mode around a classical amplitude plus some fluctuations. And these fluctuations can then be like vacuum fluctuations or thermal fluctuations. And if you do so and you plug this into the Hamiltonian before, what you end up with is a Hamiltonian with a linearized optomechanical interaction. Yeah, and you see this is again a quadratic interaction which we can control with the outside drive. And this big G is now enhanced by the classical amplitude. So it depends on how strong we drive, how strong these processes are. Okay. And the way we drive the system will determine, as we have learned at the beginning, what kind of interaction we have. And this is just a way to depict this. Here we see something which should resemble like the spectrum of the cavity, density of states of the cavity, however you want to think in terms of frequency. So we have here resonance where we are really on resonance of the cavity. And then we have something which we call sidebands, the blue sidebands, which just above one mechanical line width of frequency above the cavity resonance. And here we are below. And then we can think about driving at exactly these three spots, and all these driving at different spots will give us different physics. And I don't want to focus so much on what's happening here, but I want to focus for the rest of this talk what happens here if we drive on the red sideband. And what happens is actually that we get effectively this Hamiltonian to be resonant, a swapping of excitations between our mechanics and our cavity. And we can look at this in terms of Stokes and anti-Stokes scattering. So we have a photon entering below resonance. It can scatter up onto the cavity resonance by extracting an excitation from our mechanics, which is good, right? Because we can then cool the mechanics. Or we can have a Stokes process where we actually go down in frequency and give an excitation to the mechanics, heat the mechanics, which is not so optimal if we want to cool it. And this is what we want, because mechanics are low frequency, so they are hot objects. Even at millikelvin temperatures, they are still pretty hot. So what we want to do is actually cool, and we can quantify this balance of a heating and cooling process with actually really simple theory and derive Stokes and anti-Stokes rates. Yeah, and this is really simple in the sense that the heating rate gamma S is going to, or both rates will be connected to actually the density of states, or the spectrum, force spectrum of the cavity, the photon number spectrum actually. And so similarly is the anti-Stokes process is just at different frequencies. Yeah, so where do the mechanics sees what? You can also think about this if we say with this picture, this process here is weighted here in this form with exactly density of states at the cavity. And you see here in this nice form that the Stokes process is suppressed because you don't have so many states available in your cavity. This is what we call also the resolved sideband regime, where the mechanical sideband is outside of our resonance peak. Okay, so the photon number spectral density is, you see here for the simple systems. And important is that if we have the rate for the anti-Stokes process which is much larger than the Stokes process, we get actually net cooling. And this is only possible in this way. What we call back action cooling is omega m is larger than kappa. And you can see here that the Stokes rate is suppressed exactly for this regime. And then you can actually get net cooling. And people have done that in the lab. And this is, I apologize, this is an older picture. I know I recently learned there's a newer one now out, but this is an overview from 2014. It's also a nice review about optomechanics if you ever want to learn more about these systems, where we see here the photon number as a function of this parameter omega m over kappa, so the sideband or resolved or unresolved sideband parameter. And you see that people have, first of all, here's the ground state, right? They have reached the ground state here. But they all just, these experiments happen mainly in this regime where we are resolved. While here, nothing happens much. Yeah, you are in the unresolved sideband regime. And it's easy to understand why nothing happens here. So, because if we think about the unresolved sideband regime, we have now like a really broad cavity. And then the rates for our anti-Stokes and Stokes process, which are weighted with this density of state of the cavity, is actually, they are the same, right? And so we have, if they are equivalent, we will not have some net cooling in our system. And this is then a disadvantage because a lot of these optomechanical platforms or architectures are actually in the unresolved sideband regime, and this kind of cooling cannot work. So people have thought of alternatives, and one way is to do feedback cooling, meaning to measure the position and apply the right kick at the right moment, which I'm not an experimentalist, but I think of it as pretty challenging, and that's what at least my experimental friends also tell me. Another way of doing is using squeezing, and there are a couple of proposals here by Glau and Clerk, and also this from Vitali's group, and there's also some experimental implementation already from the NIST group recently. And what I'm going to talk about now in the next minutes is related to the squeezing or to these proposals, but it's slightly different because we don't have the control about the squeezing as is required in these ideas. So now we're going to talk actually about an experiment in the next, how many time do I have left? 5 minutes. Okay, I will try to make it in 5 minutes. Okay, so this was a recent, it's on the archive, it's a really recent work with Gerhard Kirchmeyer's group in Innsbruck, where we have a really nice system, or they have a nice system, where they have, again, an electromechanical system where we have a cantilever tip with a cantilever tip, and then you have a magnetic tip, and it's above a squid, and then this motion here modulates the flux through this loop, and this you get an inductively coupled optomechanical system. And this is a really nice system because they hope that they can get really strong coupling at some point when they already have a really decent coupling. But again, I'm a theorist, so we think about Hamiltonians. So this picture in my head is, first of all, something we have now a squid in our cavity. So we have a nonlinear cavity. We have this free energy, and we have this Kerr term, self-Kerr term, which is clearly nonlinear. And this is combined with our moving part via the normal optomechanical interaction, right? And this Hamiltonian, I want to denote for such a circuit, was already derived by P.D. Nation and others in 2008. So we did not derive that. This is something which was already clear. And in addition, as normal, we will drive the system with one tone. So this is then the full system description. And this is non-trivial if you want to, like this is a nonlinear system in two ways. You have a nonlinear cavity and then, in principle, nonlinear optomechanical interaction. So what we did is actually the same thing as we normally do. We have a displacement transformation where we have now a classical amplitude. And this time we really have to take that into account. Like in a lot of theory works, we like mainly disregard what's happening here and focus on what happens to the fluctuations. But for this particular system, we actually had to think a bit harder about the classical amplitude. And I want to explain this in a second. So here, this is the expression, the classical dynamics of this amplitude, which you see here. This is the nonlinear term. This is just some input like drive, and this is just damping and some detuning. So important is this nonlinearity, and this is this effective Kerr constant, which involves a Kerr which comes really from the circuit, the Hamiltonian we saw. And we have as well something like a mechanical mediated Kerr, which is always there in an optomechanical system. Important is that this equation here, or this dynamics of this cavity classical amplitude, is actually something which is has for a long time just one solution, but at some point there is a bifurcation happening. This system becomes bistable, and this happens, for example, for a critical input flux. And if we take a look at this critical input flux as a function of G, to get a bit of an idea about how important this mechanical curve is, what we see that this critical input flux actually stays for a long time, like pretty constant, and is independent of our G. So this part doesn't play a role for a long time. I have to denote we took here a Kerr constant related to the experimental parameters. And we can also see this if we just simply look at what happens if we would not have this Kerr and how high the critical input would be, and you see it's huge, right? To really achieve or like really go into this regime where this term plays a role, you have to drive either really hard or have a really strong coupling. Here you see that at some point this mechanical curve will win and will dominate what's happening. And to orientate you, this is where we are in terms of the experimental parameters. I will give them to you in a second. So we are really at a point very far away from this part playing a role. And I will also, all the examples I will show, I will focus on the experimental parameters. So clearly there's a huge parameter space here, but I will focus on this part. Okay, so this is the next step is going to think about, okay, how is the photon number or the average photon number in our cavity look like as a function of our detuning? And to show you, first of all, like if we would not have a curve, what we would have is a really symmetric density of states in our or like photon number in our cavity. We have a certain like a symmetric Lorentzian. If we include the curve, before I say that these are the experimental parameters, okay, so keep them in mind. I will not show them again. Important is that we are in the unresolved sideband regime, and we will drive close to the bifurcation. And if we then, first of all, take a look exactly what happens if we are in this parameter regime and look at the photon number, you see this form has changed a lot. So we are shifted and tilted. This is what we call the shark effect. Okay, and you will see the shark again, and I will show you this shark effect is really important to understand what's going on later. Okay, so this is the photon number. This is the classical amplitude, and we will account for the classical amplitude in all what follows. But then this is the other part, is the fluctuations. So as you perhaps remember, the Stokes and anti-Stokes process will be related to a force spectrum, which we calculate via looking at the fluctuations. So we have to actually look at how is the dynamics of them. This is again a Hamiltonian which is linearized, where we have it first of all a squeezing. That's how the squeezing comes in of the photons. And important is that now this squeezing strength is actually the product of the square term times alpha squared. So we have a photon enhanced single mode squeezing. And we combine this, or the optomechanical interaction is also enhanced. And so this is now this big G again, where we have now, again, a photon enhanced optomechanical coupling strength. And I point this out because the shark will become relevant for both of these strengths. But first, let's look at the force spectrum, which will then be related to the rates for our scattering processes. This is now the situation where we have no detuning. Again, if we would not have a curve, we would have a nice Lorentzian, and something completely different goes on if we think about this Kerr oscillator. So we have here shifted, Kerr shifted maximum, it's much lower, and it seems like we have a double peak as well. So it's really like a completely different kind of force spectrum as in the linear case. And as a reminder, we have to, it's like the mechanics, this is the environment the mechanics sees, right? And from this, we can extract the rates for the process of cooling and heating. And if you now take a look at this, exactly at the mechanical frequencies, so this is here the heating process, Stokes, and you see actually that this is enhanced. So the Stokes process is here, this is really just multiplied by this value of the force spectrum. And so you see that in this regime, we would already be heating the mechanics and not cooling it. In contrast, if we now go and detune, so we go close to what we call a critical detuning, the situation is reversed. You see now that we have our Lorentzian, we have something which is not a Lorentzian perfectly, but something similar to Lorentzian, which is now centered again at 0, and our anti-Stokes process is enhanced. And you see in contrast, the linear case is shifted now, and it's really broad. And one important thing is actually this narrowing, because somehow we shift ourselves into more resolved parameter regimes. And to understand this noise spectrum, or this force spectrum a bit better, we can take a look at the poles of the system. Yeah? I don't know how familiar you are to think about poles, but poles give you really a nice idea about how spectrum changes and how the form of spectrum changes. And this has this really interesting structure, because what we have here is just the real part and the imaginary part of our poles. In the end, is related to the eigenvalues. It really describes the dynamics of the systems. We have two special points here, which are exceptional points, where we have the degeneracy of your eigenvalues and eigenvectors. It's a specific point in open systems. And just as a simple point, if I look at this kind of behavior, what I see in this regime, when I have a detuning of this form, I will expect that I have two peaks, yeah, with one damping. Yeah, and they can be lying over each other, or they can be split. That's not visible from this part alone. But in the end, you have a two-peak spectrum, and here as well, or can have a two-peak spectrum. And in the middle, we have exactly this point where we have this single peak, but with two widths. Yeah, so it's like a product of two Lorentzians with two different damping rates. And important is what we see here, that we artificially, or by this nonlinear system, what happens is actually that one of these damping, or these imaginary parts, actually goes up and goes close to zero. And this is like an amplifier. What happens is we narrow down or we are focused on the resonance, but we get narrower and narrower. And this is something like the photons stay longer and longer in our cavity. It's related to the bandwidth. So we have a critical slowing down, similar to a phase transition. And this is exactly the point where we want to operate. And to see that this is really the point where we get the strongest damping, we can take a look at really the optical damping. And you see exactly at this point, we have a strongly enhanced optical damping, which is much stronger than in the linear case. And to not stick too long here, let's go to the result. If we think about the mechanical occupation, this is the main thing we want to look at. We are really like I think like 3,000 phonons. And then we look at, okay, what happens if we turn on our interactions. So first of all, this is what we expect from the linear case, no curve. Right? You can go down from 3,000 photons to 132. It's far away from the ground state. If we now include the nonlinearity, but forget about the shark, we can actually do better and go down by a factor of 2 to 70 phonons. But the shark is important. If we include the shark, we see actually that we can get a factor of 10. So what happens is really this, that we can enhance the cooling to not to the ground state for these experimental parameters, but we can go pretty close to it. And for the experts, if you ask now how far are we away from any kind of limit, the back action limit, we are away from that. So the back action limit is the point where you can't get lower, is actually 2.18 phonon. And the reason why you can't go further here is if you drive stronger, you're going to bifurcate your cavity, you become unstable. So you stay here before bifurcation. So you're limited in terms of how many photons you can put into your cavity for these specific persistent parameters. And for the last part, I just want to show you that the theory we have looked at actually matches nicest to experimental results. This is said by Gerhard Kirchmeier. You see that if they tune around the cavity, this is a bit of a different scaling, so don't be confused. They can go and tune here to the lowest number, and you see that the theory matches for this part, cooling part, really nicely to our predictions. In total, what they achieved in this experiment was 14 phonons. It was the limit they could get with the current setup, and they were mainly limited by flux noise. We hope, or they hope, to do better next time. Okay, so to wrap up, I want to acknowledge the funding, and most importantly, the experimental collaborators is Gerhard Kirchmeier. The experiment was done by students, Lucas, David, and Christian, and also in collaboration with Mathieu Juin from University de Sherbrooke. And last but not least, I would like to acknowledge my group, which is now a hybrid kind of situation, still in Berlin, already in KIT, already in Strasbourg. Nico Diaz was the person working on the collaboration with Gerd Kirchmeier, so all the calculations, the work was done by him. And we are looking for postdocs, PhD students, and master students. So if you're interested, come talk to me or write me. Thank you.
Thanks a lot, Anja. Thanks a lot. It was, I mean, really few questions. So like really, really good. So now, yeah, we have.
So thanks for the talk. It's a question that I have for a time since I read that paper. In the plot where you show the mechanical occupation, what the linear projection means. So the next one.
This?
Yeah, what linear projection means there?
As far, if I remember correctly, this was in the end really just using the linear theory, and it did show it worked. Or you see, that doesn't work. It does not explain what's going on. So it's just remove, like not including the shark, okay, not including the nonlinearity correctly.
Okay, so it's basically you just linearized all the equations of your Hamiltonian.
Yes.
But then to calculate the steady state, you don't include the kernel linearities. Is that, or you just don't include kernel linearities at all?
As far as I remember, it does not include the shark.
Okay, okay.
Yeah, so I would have to check, but we will see each other again, right?
Yeah. Okay. Thank you.
One more question, two more questions. Yes.
Anja, I have a question regarding the first part of your talk, because you compared yourself to circulators as they are out in the vase and in the experiment. So my question is relating to your reservoir engineering. Can you give us some hint if you see chances that we can engineer this in a suitable experimental environment so that the frequency span of nonlinearity can, for example, span several gigahertz? Do you see that this is in principle possible, or is this just kind of?
So you want to build a non-reciprocal transducer, or?
I would like to build a non-reciprocal transducer. If with amplification, I'm more happy, but even without,
we can, like, theoretically that works all. You know, like so this is I can give that to you later, but the thing is, can you engineer the processes, right? So there has been actually some proposals about doing non-reciprocal transducers which exactly match that recipe, right? You have to get to couple you get all the parametric processes, right? So if I have two really different modes in terms of frequency, if I can get them to talk directly to each other, which is hard if I would think of them as being gigahertz and terahertz mode, right? So this is then hard to get this process directly. The one thing you could think of doing is doing this with a 4-mode system, and then you use perhaps 2 mechanical modes to get exactly this non-reciprocal coupling between these the high and low frequency mode. So with a 4-mode setup, you have perhaps a chance to do it, but you have to apply at least 4 tones, if not more. So it's.
And my question, if I may, would be: so you focused on Markovian bars. What would happen if you kind of relax this condition?
Nothing bad.
Or is it kind of the wrong way of looking?
No, it's completely right. So I use this Markovian limit because this is the easiest way to, I give you a master equation, it's the easiest way to see what's going on. But as this experiment with Oscar Painter was not in that regime, right? So, and what happens if you are on a Markovian limit, you're really directional over all frequencies in theory, right? So you're really broadband in terms of isolation. If you start to see non-Markovian effects, you're going to you're only non-reciprocal at one frequency, and then there's a limited amount of bandwidth where you have good isolation. And this is not such a problem for an isolator, but if you think of having also gain, and then this effect is is harder. Like, you know, your bandwidth is smaller.
So Alex, short last. Yeah,
Yeah.
well, if it's longer, then
I
we
also want
continue
to
the
have
coffee
some
break.
coffee.
But,
So.
yeah.
Yes, thank you for the nice talk. I'm trying to relate your theory to one of our experiments. So in this limit of balanced coherent and dissipative coupling, is there any hallmark signature in the frequency domain? One would say here the sweet spot has been reached. You know, the three oscillators?
Yes.
Right. So if you reach exactly this point of balanced coupling, what would be the signature of the oscillators in the frequency?
So, okay, so.
Is there any spectral?
Yeah. So you would, okay, I'm not sure if but obviously you get this either at the noise or at just a scattering behavior, right? And the moment you see exactly, you have to see an asymmetric scattering behavior depending on which direction you put your signal in, right? So I go through in one direction, or I don't go through in the other.
Yeah, this is kind of a spatial signature, a spectral one, like line narrowing or, I don't know, signal enhancement of one of the oscillators.
This depends on what kind of interactions you would have. But okay, perhaps we have to translate my theory thinking to your experimental thinking. But we look at this as do you think in terms of that I should think of it as noise spectra, or do you think, because we look at everything in a steady state, and so we look at spectrum as a function of frequency, right? And you see this asymmetric behavior, and you should see the same asymmetry if you look also at noise spectrum. And so I don't know if you come together in terms of language, but I think that, yeah, but there are, I'm sure if we find a point to, you know, where we can talk.
Now,
you will,
in the coffee break,
Yeah.
you will reach.
Thank you.
Yes, thanks.